Hey everybody, welcome. My name is Caleb, and this video is going to be basically an explanation on how proof of work actually works. So in other words, how Bitcoin mining works. So proof of work is known as a consensus mechanism. Why do I have a circle and an AI on my chalkboard? Anyways, basically this is a consensus mechanism, a way for all of the nodes to agree on things. And the consensus mechanism of choice that we're going to be talking about in this video is known as proof of work. So instead of having a centralized entity confirm transactions, this is what Bitcoin and other blockchains use to confirm transactions, or to confirm blocks of transactions. Before we get too deep into this, I wanted to give a special thank you and shout out to our sponsor. Crypto.com is a simple app to buy and sell cryptocurrency. With one of the largest selections, this is the perfect app to explore different cryptocurrencies, their prices, and information about them. Additionally, you're able to stake your cryptocurrency for consistent growth in your balance. Best of all, Crypto.com is known for their Crypto Rewards debit card. Get crypto back for every purchase and get started for free. Sign up with the referral code Caleb and get a $25 bonus when you stake for the Ruby debit card. Look for a link below. So thank you Crypto.com for sponsoring this video and my other cryptocurrency videos. Be sure to check them out. So before we understand proof of work fully, we need to understand what's known as a hash function. Now we've talked about these a ton in some of my other programming videos, but this is really important in proof of work. So I'm going to draw a hash function as a square, or technically it's a rectangle, sorry. This is our hash function. And a function will take an input and give an output. So in a hash function, we have some input, and the output specifically is known as a hash value. And it's pretty much just like a bunch of random characters. It's not something you can read. And basically, what it'll do is it'll be a one-way process to take some readable input and give us some not readable output. So just as an example, we might hash the string Caleb, and the hash value might look like, I'm just gonna reference my notes here, I don't have it memorized. B3A0F1 F, and it's honestly just going to keep going for 64 characters in this case, and it really depends on what hash function you use. A really popular one is SHA-256, and this is going to give us a 256-bit hash value. Now the thing that's important about this is that if you take that same input and ran it through this hash function again, you're going to get that same output. So you can basically look at this output and you have no idea what input gave us that value because it's just a bunch of random characters, right? But you can go the other way where you take an input and confirm that it gives us that output. This is the same functionality used when you try to log into a website. You might take your password, let's just say it's pass. This will be processed through a hash function, and then the result of that hash function will be compared to the hash function that's stored in the database. And the benefit here is that you can easily confirm if they got the right password, but you don't actually store that password in the database. So it's the same functionality that's going to be used in proof of work. That's exactly how a hash function works. One of the most popular is SHA-256. This is a version of SHA-2 if you want to know more information. Now I mentioned this will be 64 characters, but then I said this SHA-256 is going to give us 256 bytes. So what's going on here? Well, basically each one of these characters is known as hexadecimal. I'm just gonna write hex, it's a little bit easier. And one hex digit coordinates to 4 bits. So one hex digit equals 4 bits. So as an example, we might have the binary 0011, which is the value 3. We would represent this in hex with the value 3. We might also have another one, 1111, which is 15. And we would represent this in hex with an F. So hexadecimal is just a condensed form of binary, if you think about it. You can represent 256 bits in only 64 characters. So now that you have that prerequisite knowledge, we're going to build up an example that starts off a little bit silly. I swear. It's gonna be a pretty silly example to start, but we're gonna continue to add layers, and then by the end of this, you're going to fully understand Bitcoin mining. So it'll be pretty cool. So basically, we're gonna play a game. I like games. Let's say we have some hash function, and I want me and you to compete to see which one of us can get the first value under 500 here. So the goal here is to get a hash value below 500. All right, start. But there's one extra condition of this game I forgot to mention. The input to this theoretical hash function here has to be tacos. All right, the string tacos. So we both take the string tacos and pass it into this hash function. And let's just say we both get the value 505. Uh-oh, we lose. Both of us lose because neither of us have met this condition. That's weird. Like, why am I making you already know what the input is? I'll explain that soon, but basically that's one of my requirements of this game. It has to have the value tacos as the input, and we have to have a hash value below 500. Those are the rules. So, because this game is very important, we start conjuring up, what can we do to make this work? What if we include tacos, but not just tacos, we add a little bit extra in there? So let's say we try tacos 0. And let's just keep track of what outputs we get here. Let's say tacos gives us the value 505. And just if you're confused how this number coordinates to binary or hexadecimal, binary and hexadecimal is just another way to represent a decimal number. It's just different forms of representing the same thing. So you can just think as the output as some really large number, but this is just a theoretical hash function where the numbers are really small, just for our example. So tacos gave us 505, and let's just say tacos 0 gave us 530. Well, at least now we have some variation. There's a chance if we keep trying different things, we'll be able to get under 500. Let's say we both try tacos 1 and we get something like 504. We're getting close, not quite there. Tacos 2, 709. And then we try one more option here, tacos 3, and we finally get a value such as 409, which meets the qualifications to win the game. So whoever managed to guess tacos 3 as the input first wins. Now, obviously, since I'm really competitive, I'm probably gonna win, so I calculated these very fast. So I beat you to guessing this hash value, so I'm the winner. So that is how we win. We basically try a bunch of different variations of the input, and the first person to get that output wins. But this introduces a big problem. Now, obviously, I'm a beast. I beat you in this competition, and I'm just gonna keep beating you because I'm just faster at computing these. You know, maybe I set up my computer to be really fast, and I win every single time. Well, that's not exactly fair because we basically have one winner every single time. Nobody wants to play that game, and that game's not gonna last very long. So, to fix this, we introduce even more variation to the input. Now, instead of having me and you calculate tacos as the input and then just changing a little number, we're going to have to calculate this using our first name, just in theory, or some piece of data that is different for each person. So instead of tacos for me, I'm going to use Caleb, and that's going to completely change all these outputs. So let's say Caleb 0 gives us 934, and then let's say Caleb 1 gives us 572. Caleb 2 gives us 605. And then Caleb 3 gives us like 836. And all while I'm doing this, you're doing the same exact thing with your name. So we'll write those over here. Let's say your name is Ali. So Ali 0, this might give us 730. Ali 1 might give us 930. Ali 2 might give you 800. And then Ali 3, let's say, gives you 300. And you win. And even if, in this situation, I got to Caleb 3 faster, well, that wasn't a good enough answer So if you were just a little bit slower, but you were the first one there, you still win. You know, I might have been all the way up to Caleb 300 and still haven't calculated a hash value below the requirement here. You might have gotten on your first try. So introducing that variation, not only with these numbers, but also variation between the different players, now it's a more fair competition. You know, Caleb can win, and in general, because Caleb is faster, he's going to win more often. But Ali, you, still has a chance of winning because it's more randomized. If let's say I was twice as fast at doing these calculations than you, well, I'm gonna win about twice as often. However, because of the variation, you're still going to win sometimes. All right, so this is just a silly, stupid game. So what I wanna do now is I wanna look at each one of these components and see how this correlates with Bitcoin mining. These participants, this one's me, and this one is you. These are known as the Bitcoin miners. They are the ones playing the game. So these are the miners. This hash value we are trying to get under is known as the target. This arbitrary number that we're just incrementing is known as the nonce. I'm running out of places. Okay, this one's gonna be a little off to the side, but the nonce refers to that number that we're just incrementing just to add some variation. And then instead of actually using the first name here, we will have the transactions of the block where one of the transactions is paying the person who wins the competition. And this is known as the Coinbase transaction. So in Ali's case here, Ali will have a transaction paying herself. In my case, I'll have a transaction paying myself. So the ledgers are different, so it introduces that variation. And last thing, instead of using really small numbers like 500, we're going to be using astronomically huge numbers. Remember that in Bitcoin, it uses double SHA-256, which means the output can be up to 256 bits long. And if you just want to know, you can go ahead and look up the max number for a 256-bit number. It's really big, and I'm not going to try and write it out. So now that you understand a little bit about how this little game works, it's still a little unclear how Bitcoin mining works. So let's kind of go through this example again using Bitcoin. I drop my chalk every video, I swear. Let's go through this example again with Bitcoin. So we are both Bitcoin miners, and we're competing for that sweet, sweet coin. So instead of having our name or some really silly thing being what makes variation, we're going to have the transactions. So this is the block with all the transactions that we're trying to confirm. And you have one as well. And they're slightly different because, again, mine is going to reward that Bitcoin mining reward to myself. Yours is going to reward you. So the hash is going to be different. And the way that this process works is we build a Merkle tree. Now, I'm not going to get into all of the data structure stuff here, but here's a quick intro on how that works. Let's say we had 4 transactions, A, B, C, and D. Bitcoin takes the double hash of each one of these. And I'm going to write that as D hash. So D hash of A, D hash of B, D hash of C, and D hash of D. And I'll just assign these to variables: D1, D2, D3, and D4. Then we basically combine these. So we're basically trying to get just one value, so we have to combine these 4. So let's just say we have D5, and this is going to be the double hash of D1 plus D2. And then again, we'll have D6 be the double hash of D3 and D4. All right, we're getting closer. We're down to just 2 now, but we still just need to get 1. So let's say D7. And that's going to be the double hash of D5 and D6. All right, there we go. And this value, that final hash value, is the Merkle root. So we have the Merkle root, and just to basically say that these are going to be different for me and you, let's say this transaction here is that Coinbase transaction. In mine, this transaction would be paying Bitcoin to me. In your block, it would be paying Bitcoin to you. These both can't be true, so we both have to compete to see which one is going to win and be the official block added to the blockchain. But you can think of this Merkle root hash value as a summary of all of the transactions. If you were to change just one of these transactions, that would change that Merkle root, because all of the hash outputs are inputs to the next hashes. So if you visualize this as a tree structure, changing any one of these nodes in this tree is going to ultimately change that top node. And that's just a basic way to confirm that, hey, none of these transactions were tampered with because the hash value is the same. But I'm kind of getting a little too deep into this. That's all you just need to know. This is the Merkle root, and it's basically a summary of all the transactions. Your Merkle root on the block you're trying to confirm is going to be different than the one I'm trying to confirm, and that introduces variation, which makes it possible for anybody to win, not just the fastest computer. That's not the only variation. There's also a timestamp and that nonce we talked about. So basically we take this Merkle root value and we throw it through the hash function. Oh, it didn't quite meet the target. It's a little too high. So we just increment that nonce and we just keep doing that until we get a value that is under that target. Now the nonce isn't the only thing we need to introduce variation, and that's because the target value can be very high. We might need to make a lot of guesses. And that nonce is only a 32-bit number, which only gives us a limited number of possibilities. So basically, we just increment through that nonce as much as we can until it overflows and restarts from the beginning. And at that point, there is an extra nonce in the Coinbase transaction. That'll get incremented, which will change the Merkle root and introduce more variation. Basically, we don't ever want to repeat calculating the same exact inputs because it's going to give us the same exact output, which we've already tried. So every time we try to guess this hash value, we need to introduce some variation. That's done through the nonce and then the extra nonce. So if we cap out the nonce and at that point we've tried everything, well then we just change that extra nonce in the Coinbase transaction, which changes the Merkle root, and it allows us to start this nonce again from the beginning and go through that same entire 32-bit range of options. So again, a lot of detail here, kind of takes some extra background with overflow and all these different computer science concepts, which you can get all that information on my channel, but just trying to give a pretty good overview that's somewhat technical. Now, I'm also not an expert on this either. There's people that develop this algorithm, and you can get all the source code and stuff if you want to know the super details, but this should be a pretty good intro. So if you didn't figure it out by now, proof of work takes a lot of work. It's done very quickly on your own machine, plus all of the other Bitcoin mining machines in the entire network. And this takes on average 10 minutes to confirm a block. So with all of the computational power of the network, it's going to take 10 minutes. Now, that being said, this 10-minute number is defined in the protocol, and it's not so much that that's just how much work it takes. If we double the computing power, it's not going to make it twice as fast. The time to confirm a block is going to remain 10 minutes. And if we do double the computing power, basically what's going to happen is the difficulty is going to be adjusted such that it stays at 10 minutes. How exactly does this adjustment take place? Well, that target hash value, this can be increased or it can be decreased to make it easier or more difficult, because we have to get under this target value. So if this target value is really, really high, it's going to be fairly easy. But if this target value is really low, like let's say you had to get a hash value under 5, that's going to be extremely, extremely difficult. So this target is adjusted over time to ensure a 10-minute block confirmation time on average. So it takes a long time, but to actually confirm it is very easy. Once you have the correct hash value that meets the qualifications, checking it is very easy because you can just test all the same inputs and confirm that hash value. And that's the beauty of hashing, is going the other direction. Starting with the hash value and figuring out the inputs is very difficult. But if you have those inputs, you can process them through the same exact hashing algorithm and get that same hash output. So if a miner is like, yo, I figured it out, well, then all the full nodes can confirm that by testing to see if the inputs give that same exact hash value. Again, this is exactly how password checking works for websites. You give an input for your password, and the web server doesn't know if that's your password or not. What it does is it just runs that through a hashing algorithm and then checks to see if the values match with the hash value in the database. So the database doesn't actually store your password, it stores the hash value of your password, which if you have that hash value of your password, you can't easily check to see what the input is. So that was an introduction, but there's still a lot we didn't cover. You know, how exactly is the target determined? What's the difference between target and difficulty? And what about mining pools? There's so many different questions. So we're gonna continue this discussion in this series of videos. So if you want to get the full story, then be sure to check out the playlist of all of the Bitcoin and cryptocurrency concepts. Basically lay that foundation for everything you need to understand new cryptocurrencies and the difference between the different cryptocurrencies. And overall, it's a great playlist in my opinion. So please be sure to check it out. And if you enjoy this content, please be sure to subscribe and go sign up for Crypto.com. Get one of your Crypto.com debit cards. Thank you for watching. I'll see you in the next one.